This is the second of 3 videos on the elements and how they're used in the synthesis of some current organic compounds in medicines, agriculture, or how they're used in new technology. So I've tried to make this a little more interesting than just some of the stories you might have heard in your high school textbook about, let's say, lithium being less reactive than sodium towards water. Well, there's a lot more being done than just adding lithium to water. And we've covered a little bit of the alkali and alkaline earth metals, so it's kind of in the last video, just to kind of summarize. We talked about S block metals, and we focused in on lithium, which is just below hydrogen. We also focused in on catty corner to it, magnesium. I just want to clarify something I said regarding the other class alkali and alkaline earth metals. It's only magnesium and lithium that can make bonds to carbon directly. They are part of the group 1, group 2 metals, but they are those unique, metals because of their their charge density. They can make bonds to carbons, be soluble in non-polar solvents or somewhat polar solvents, and be used in organic synthesis. You can't do that with sodium. You can't do that with calcium. Those metals will not bond to carbon. So every other group 1, group 2 metal, other than magnesium and lithium, cannot make a bond directly to carbon. They can bond to carbonates. They can bond to phosphates, and don't get me wrong, we can do a lot of good chemistry, inorganic chemistry, with calcium and with sodium and other group 1 metals, group 2 metals. But I just tried to make sure you knew that there are some alkali metals and alkaline earth metals, magnesium and lithium, that can be used in some very cool organic synthesis reactions. I'm going to touch on that a little bit more in what I'll call a sort of in between the second and third videos. I have a story we'll tell about lithium and copper in their use in organometallic chemistry. Well, let's focus. Let's keep our eye on the ball for this second video. We're going to look at transition metals now. We're jumping from the S block. We talked a little bit about, again, magnesium and lithium and how they're so special, bonding to carbon. We're going to go to the D block now. We're jumping into the D block. Transition metals, and you want to remember that transition metals have, as far as electrons, those d electrons of varying number, and they also have the s electrons. So you've sometimes seen it, let's say if we're on the first row, you'll see it as 4s, then you'll see it as having 5 of the 3d electrons. Just want to say something at the outset. One of the common charges you see for transition metals is a +2 charge, whether it be for cobalt or iron or copper. You'll sometimes see that because what happens is, being a 3d, a third level d orbital, when you start taking electrons out, this d level starts to drop below the s level. And so you commonly will have 2 electrons that can be considered as taken from the 4s orbital. Just remember that. A common charge for transition metals is +2. But that said, there's a lot of other oxidation states you can have, or charges for the metals. And man, there's just some really cool chemistry that goes on the surfaces of transition metals that are heterogeneous, where you have an actual piece of metal or flakes of metal in solution, and there's chemistry that happens at the surface, or what we call homogeneous transition metal catalysis, where the metal center, I can bring my fingers here to say this top is the metal center, and there's molecules around just one metal, and what you can get is binding of not just oxygens and nitrogens. These transition metals, like the magnesium and lithium, can allow for carbons to be directly bonded to that metal surface. That's why I kind of wanted to start off saying no other metals in these 2 columns besides magnesium and lithium can bond directly to carbon. But boy, we see a lot of that in the D block. And that's going to be very useful in synthesis of smart materials. So that's where we're heading. I'll also talk about some just cool properties that you get as far as strength and color with transition metals, but I'm going to spend more time looking at the catalytic chemistry. So we just said that you can have some strength added to your metals sometimes by just adding these into iron as an alloy, or sometimes you'll have carbon added into iron to make steel. It's because transition metals typically have a pretty high density, high melting point. So these are the things you want to have with building materials: strength, and not just like plastics necessarily. You don't want necessarily the flexibility. That's one application. You can also, with transition metals, use them for inorganic dyes. If you look at some of your paints and what dyes you use, they have metals like cobalt or zinc with oxides around them, or with cyanide around them, or with aluminum oxides around them. So what you get is a colorant that's because the dyes have this transition metal present. And based on what's around the metal, as what we'll call either ligands or ions, can change the color. So a lot of your inorganic dyes are used in paints because they're not as susceptible to oxidation in the sun or in some intense sunlight with heat, like your organic dyes. They are susceptible to oxidation and loss of coloring. So we'll talk about that. Now, I do want to just say there are some links that you want to click on under this image. I know there's two under these two videos or articles that you can check out. Please check them out. The first one here is a video, and it's really cool because you get with platinum or palladium or nickel. You can use these as, I guess, catalysts for all kinds of reactions. One of them I'm just going to show is using platinum. If you go to the video under this symbol here for platinum, you'll find that this video talks about a reaction where they can take oxygen in the presence of the platinum and oxidize the ammonia. I'm going to put it up here so we have a little more room to give us 6 water molecules plus our 4 nitrogen monoxides. Now, if you look at this, it's kind of 9 total, plus 6 plus 4 is 10. So we kind of have an entropic driving force here for formation of this, it seems. But also remember how I said that if you form water, that's often enthalpically a driving force for the reaction. So don't know the numbers, but I'm guessing that this is not only entropically driven, but enthalpically driven, because we are forming water as a product from this ammonia with oxygen reaction catalyzed by platinum. This next one is a very important reaction. It's the Haber reaction. And Le Chatelier influenced some of the work by this fellow in Germany as a chemist. He figured out how to, this was huge, to make ammonia from nitrogen gas, which was very, very hard to do. We talked about that in the last presentation, that it's just a very stable structure. And over iron surface at higher temperatures, you can get ammonia to form. And if you can pull this out of the reaction, which they figured out how to do through, it's very polar, so it tends to thankfully grab itself and come out as a different phase. You can sort of siphon that off and keep the reaction going, because the reaction works against that change. It'll continue to make more ammonia. If you watch the video under this, I guess, box here, you'll see that discussed. Really cool. These are examples of heterogeneous chemistry where those gases are drawn in onto a surface of some metal. They are coating the metal surface, you might say, or bonding with it. Now, kind of an illustration here where you have nitrogen has come down, it's broken a pi bond. You had three bonds, but it's broken and starting to bond to the metal. We can break completely the nitrogen bond, have it now sort of bonded just to the metal, and then we can have some of these hydrogens start to come in, react with this to make that NH3. So that's kind of how it works. You get the gases absorbing to some degree onto the metal surface, and then they come together and they can make some new structures and kick that off. It's really cool chemistry that you can do with these metal catalysts that are heterogeneous. But you can also do some really cool chemistry with a metal center. So we have one palladium metal center here, and these L's represent ligands. So you might just kind of remember that L represents a ligand. You say, well, what's a ligand? It's like a covalent bond, but we don't change the sign. So let's say we had NH3, which is a common one, and that was our ligand. When we put the N on this, we wouldn't make the N positive, saying it's changed its number of bonds. It's just sort of coordinated to the palladium. It's a different kind of sort of discussion or thought where we take this NH3 group as our L, and it's coordinated to the palladium, but we don't say, well, because it has another bond, we'll make it a positive charge. You don't do that when you're talking about ligand chemistry. But long story short, the key about this, if you go to the video underneath this image here, you'll see that this is so cool. They can connect this carbon right here to this carbon right here in the end through this intermediate. That is phenomenal chemistry. Usually you can't make these two carbons connect without some really serious effort and a number of steps. This all does it fairly easily in just one step, or one reaction solution which has a lot of steps. You can get, works it out by itself. You get these two carbons to connect to make, and I'm going to just put it underneath here, a carbon-carbon bond, but not just any carbon-carbon bond, but a carbon-carbon bond between two benzene rings. And I've drawn the circles here because you'll sometimes see that represented instead of double, single, double, single. This is the same thing. This is, wow, kind of phenomenal that you can do that kind of chemistry with these metal catalysts. And I keep this video short. I'm going to let you have fun and look at this one here. This is work that was done to make polymers out of homogeneous catalysts. You say, what's the difference between homogeneous and heterogeneous? Well, homo means it's in the aqueous, or in that, not aqueous, sorry. Most of these are non-aqueous solutions you have to use, but it's in the solvent. You can't see it. But if I throw a piece of metal into some solvent, like diethyl ether or something, I'll see that piece of metal. That's the difference between hetero and homogeneous catalysis. One's a metal you see as a separate phase. The other one is a metal center, one metal with ligands around it, or R groups around it that are going to attach, that come together around that single metal center. Now I need to keep this short, so I think this is my second to the last slide. We're going to stop. Sorry, we got 3 more, so I'll go as quickly as I can. I'm not going to spend too much time on this one. You want to check out this link on metallic glass. So besides making steel and iron and such through the transition metals, maybe with some alloys added, you can also do something that's really cool. You can take metals and with a fast cool, this is cool, you can take and make sure that you don't have phase boundaries, because as we form solids out of transition metals, you tend to get these phase boundaries where this is crystallizing, but then this is at a different sort of crystallization mode, and they meet and they, I guess, bind to each other in a weak sort of fashion. That's a weak spot. It can crack. So what you can do to get around that is you can take a really, really hot solution of your transition metal, maybe some, again, alloy and carbon or whatever, and you can have those little added elements in there, and you fast cool it so you have disorder. You don't have any phase boundaries at all, and it is so cool. If you check out the link under this I guess text here, metallic glass, it is really cool what you can do with some of those metallic glasses that are being made. 2 more, we're almost done. Real quickly, in this case you've got a nano, I guess, sphere, and it's made out of platinum. So they've taken platinum here and they are coating it with silver. So the silver is useful because over in this picture, hydrogen will absorb onto the surface very, very quickly. And you'll have also the absorption of either triple bonds or double bonds onto this, and they'll completely be sort of broken, the extra bond here and the 2 extra bonds here, and you'll get hydrogens in place of those double bonds, and it's not very selective. But what they've done, and you can check it out in this article, it's about halfway through that article, you don't have to if you don't want to, but they take silver and they coat on a nanosphere of our platinum. They can take, or it's palladium, either one of those two are often used, but I think it's platinum. They can take and put silver on so that we don't get a continued reaction to make our alkane. We go from what's called an alkyne, and we stop and leave 1 pi bond, which we call an alkene. And it's a very selective reaction. It puts those hydrogens on across from each other. So that's called a cis arrangement. That's getting really messy, but they're on the same side. The hydrogens came onto the double bond on the same side. And this particular nanosphere has been very good at keeping this from going on to further reduce the next pi bond to that structure we have over here where there's no pi bond. So that's really cool if you want to check that out. That's, again, using catalysis, but this would be a case of a heterogeneous catalysis because even though our eye can't see it, it's not at the molecular level. So kind of still maybe under that category of heterogeneous catalysis. And last but not least, this was work by Sharpless, and he won a Nobel Prize in 2001. You have a dimer where you have your metal center titanium here, which is a transition metal. And you have these ligands. This oxygen here is in a double bond to this carbon here, but it has just a very weak coordination to the titanium. It's called the ligand effect. And we also get this oxygen here, which is bonded to this carbon and also bonded to this titanium. It's hydrogen bonded, or just a ligand effect to this titanium. So you get two of these for each of the titaniums. And I don't know if I need to go into too much detail, but the coolest thing here is that with his particular homogeneous catalysis work, he could make, and I'm just going to show you the model for this epoxide. They call that an epoxide. He made, if I get this right here, he made this one right here, where the oxygen's to the back. And you do not get the, I guess, sister of this one where this oxygen's to the front. So if you can kind of see that, these are like mirror images of each other. Put them like this. So this is very important chemistry and I guess synthesis work. You have to sometimes make not necessarily something bond to a particular place, but a particular orientation. Because if you look at these two, they're pretty much the same. I can hold it up here. They're pretty much the same. It's just about where these oxygens are oriented in space. In this case, it's kind of down. If I put it in the same orientation and compare it, now that oxygen is up towards the, I guess, camera here, and this one's down towards the back. And you say, well, that's not a very big deal. Oh, it is. We call it chirality, and your body does it like easily with the catalyst, the proteins. But we're just kind of catching up to what the body can do using these homogeneous catalysis that Barry Sharpless and others have made some different types of what we call chiral transition metal catalysts. All right, thank you. Bye-bye.